Hello everyone. In this video, I'm going to go through what happens to the wave function solution when you're talking about a region where the potential energy is constant. And this is basically leading up to us working on the finite square well potential, where we'll have different regions where the potential is constant, but the constant changes over position. But to set that up, I just want to talk about what happens when you have a constant potential. So the basic equation we're starting with is just the Schrodinger equation, the time-independent Schrodinger equation, h bar squared over 2m minus sine d squared by dx squared. That's just a regular derivative of the wave function, plus the potential. And here it's going to be constant, so I'm going to call it v naught. It's not even, and it's just a constant. It's not a function of position. Times the wave function equals e times the wave function. So that's the equation that we're basically trying to solve. So the nice thing about if the potential is constant is that, the potential is constant and the energy is also constant. So we can just kind of put them together on the right-hand side as the same term. And in fact, I'm going to move all the constants over there. So let me just rewrite this, d squared by dx squared of psi. I'm just going to write psi. I'm not going to write the arguments to the function. Equals, and I'm going to have e minus v naught. And I'm going to have a minus, I'm going to put it out front. I didn't quite leave myself enough room. 2m over h bar squared, and some parentheses. Because I'm moving that to the other side, and times the wave function. So 2m h bar squared e v naught, these are all constants. So I have basically just a simple equation here where the second derivative of a function is equal to the same function, but with a bunch of constants out front. So we know what the solution to that is. And the only thing different here that's changed since when we've seen this previously is now that we have this e minus v naught, and depending on whether the energy is greater than the potential or whether the total energy is less than the potential energy, it changes the sign of this term. So if the total energy is greater than the potential energy, then that's e minus v naught is positive, but there's still this minus sign out here, and so we have d squared, the second derivative of the function, is equal to some negative constant. Let me not use k. K is a little overused. Let me use, I'll just call it c for now, times the wave function itself. And we know basically that the types of solutions to that are like sines and cosines. And so this is what we saw before when we talked about, if we just had the potential is 0 and the wave has some energy, then you just get a wave. So you get sines and cosines here, where this constant then just depends on the total energy. However, if the total energy is less than the potential energy, we still get a solution. But we just have, if e is less than v naught, then this term is negative, and that negative sign cancels this one out front, and we have a positive number. So now we have that the second derivative is equal to some constant times the wave function. And that has a solution. The solutions to that kind of equation, though, are functions that are exponentials. So in this first case, we had phi is a wave. In the second case, we have it's not really a wave. It's not really an oscillating solution, but it's an exponentially decaying one, exponentially rising or decaying. X is an exponential. So this is a little different than sort of the classical picture. Classically, it doesn't really make any sense to have total energy less than potential energy, because that basically that sort of implies your kinetic energy is negative. You can have it for a wave. It can't be true for the whole wave, actually. If you try to say the entire wave has this solution, then the only solution you get is something with 0 amplitude. But in a case where we have a potential changing, which is where we're going next, then there are places where the total energy might be less than the potential, but there's might be still a little bit of the wave kind of leaking in there. As long as, and it can do that as long as it exponentially dies off. And this leads to all sorts of interesting quantum behavior, and is the source of actually some really important physics. So I wanted to just go through, the next thing I want to do is just go through and actually just look at what is this constant actually? What are these constants? Because we'll use that. And then we'll explore the applications of this in another video. So let me clear this bottom part, because really we're just solving this equation up here. So let me rewrite this. If this is negative, so if E is greater than V naught, then this whole thing is negative, and then basically my solutions are sines and cosines, or actually, like we said, another way of writing that is that we can write it as e to the I kx. Because remember Euler's relation, we said that you can write this as cosine kx minus I sine kx. So this is really an oscillating function. And the question is, well, we want to plug this in and basically solve for what is this k? K is the wave number, the inverse wavelength, but we can solve for it in terms of the energies and all these other constants. So we plug that in, and we find that, if we take two derivatives, we get a factor of I k down each time. On the left-hand side, we get I times I, which is -1, and k times k, which is k squared, times the wave function. I'm going to cancel that out anyway, so I'm just going to write equals minus 2m over h bar. Notice the minus signs on both sides. That's good. E minus v naught. So we find that in this case, k is just square root of this combo, 2m over h bar, E minus v naught. That's something that'll come up fairly often. Did I forget? No, I didn't forget another derivative. So the other thing, well, what if E is less than V naught? Well, we could actually still write it kind of the same way. What we'd find, though, is everything looks kind of the same, but what happens is if E is less than V naught, then we have the square root of a negative number in here. So one way of thinking about it is, well, that just means k is imaginary in this case. But if k is imaginary, then it's something times I, and in fact that I will multiply by this one, and you'll just get a real exponential rather than a complex exponential. So it all kind of comes out in the end, but so we could kind of go through that way, or we could just say, well, we know from the start that it's going to come out to be an exponential. So let's just write it as e k prime x. Then we can say, well, we take two derivatives. We get a factor of k prime each time. K prime squared equals minus 2m over h bar E minus V naught. But E minus V naught is negative now, remember. So this total thing, this total combo is still positive. So we can take the square root of it and get a real number. So we get something that looks pretty much the same. But notice that in this case, we want it, this is the case for when E is less than V naught. Sorry, I missed the minus sign. There's a minus sign still in there. So actually what we can do is we can say, you know what? Since we've got a minus sign here, we can just swap the order. We can write this as V naught minus E. So that makes it a little more clear that now that E is less than V naught, that now V naught minus E is positive, and we get a real number out of here. And we can write that as a real exponential. Now I left one thing out here. Astute observers may notice. I've got a square root here, so actually, the real equation here is that k squared equals something. So the solution here, I could have, this could be plus or minus that, and I'd still have the same squares. So this could be plus or minus, this could be plus or minus. And in fact, the way we can reflect that is to say these solutions, we have plus or minus there, plus or minus there. And that's what gives us, so here we can have exponentially rising or decaying solutions. Here, they're just different oscillating solutions. The e to the plus ikx or minus ikx are just basically two solutions that are 180 degrees out of phase. But what we find is that in general, in more complicated situations, the potential is not constant. But anytime we can kind of zoom in, if we can zoom in and look at the wave function over a region where the potential is roughly constant, we should expect behavior kind of like this. So this is still a pretty useful general concept to look at. In places where the energy is greater than, the total energy is greater than the potential energy, you'll have an oscillatory behavior. Let me draw that out. In places where the energy is less than the potential energy, you'll have an exponentially rising or decaying behavior. And which one you get basically depends on what's physically realistic. Let me actually draw a more full picture. So say you have some complicated potential. We're not going to do a potential quite this complicated, but let's say, let me give myself a lot more space. Here's your potential energy. And let's say the total energy is something around here of your particular solution that you're looking at. Then what you expect without knowing anything else about this problem, what you expect the wave function to look like is you expect it to be oscillating in this region where the energy is greater than the potential energy. And how fast it oscillates or what the wavelength is depends on the details, but you expect it to oscillate basically. So you expect something that's sort of oscillating. And then what happens here? It doesn't have to go to zero right away, but it has to exponentially decay in this direction, which is actually, as x goes positive, it's actually exponentially rising. But we want it to basically decay in the negative direction because we want the wave function to go to zero at x equals negative infinity. If it blows up, that's bad. We can't normalize the wave function. So we want it to kind of decay there. And we also want it to kind of decay there. And actually, I drew a kind of an interesting thing. It might decay here, and it then might start oscillating again, and then decay again. So you can have all sorts of interesting stuff like that happen. But there, without having to do any kind of equations or solve anything, I have at least a rough idea of what the wave functions in this potential look like, even if the potential is some weird looking thing. All right. So next video, we'll be looking at the finite 1D potential well, and we've got the tools now. See you then.